Okay, I'll close this. Do you guys see the whiteboard?
Yeah.
Okay, good. So there's one thing that's, there's a couple things I thought I'd bring up first. So if we were to, I'm going to just draw a little molecule here. Let's see here. Okay, and if I was to ask everybody how many proton signals do you think you would get or have, what would you say? What would be your conclusion?
I would guess 4.
Okay, 4. Does anyone concur with that or disagree or propose something different?
I was gonna say 5, but maybe 4.
Right. So we could see we would see basically there'd be 4 different signals that we would, if we had a good spectrometer, we would see 4. So I'll label these 3 over here A. I'll label this guy here B, C, and D. So the 3 protons on the ring all are basically different from one another, right? Because proton B is basically on the same carbon as the oxygen. Proton D is cis to the oxygen. Proton C is trans to the oxygen. So all of these are basically, they've all got a special, like a different spatial arrangement with the oxygen, which means that they all have a different spatial arrangement with each other. So when we are, so they would not be chemically equivalent. Now we have the, let's see here, the N+1 rule. So if you are, let's do this, get a different color. So if you are these protons here, you've got 2 neighbors. And if you are the protons here, you've got 3 neighbors. And so the CH2s would be a quartet. And the methyl group would be a triplet. Now, when we're using the N+1 rule here, all of these protons are, when you're coupling to become a triplet or a quartet, all of these protons are, like, both CH2s are equivalent, and all of the protons on the methyl are equivalent to themselves, right? So, but what we haven't discussed is that if you look at proton, like this HB over here, how many neighbors does it have?
Looks like 2.
Right, so it's got 2. If you look at, so it's got 2 neighbors. It's got one neighbor that it's cis with, cis. And it's got one neighbor here, I'll draw it in purple, that it is trans with. Now, when we do the n+1 rule and we get a quartet and a triplet, so let's look at this here. Let's draw this. If I'm doing a bad job of explaining this, this proton, when it's coupled to this proton and when it's coupled to this proton, the coupling constant, the J, is equal because there's free rotation around this little bond between the two of them. So, and the typical vicinal coupling is around approximately 7 Hertz. So it's got, because there's free rotation around the sigma bond between the two carbons there, the coupling constant is the same for both of them. So that's why it ends up being a triplet. Likewise, if we were one of the protons on the CH2 and we're looking at all 3 of the protons on the methyl group, the J value would be the same because there's free rotation around that bond. Now, when we were talking about coupling constants before, in a previous lecture, there was a different range for cis coupling than trans coupling. So typical trans coupling, a J value for trans, was in the range of 12 to 17 Hertz, if my memory is correct. And the J couple for a cis was between 6 and 12 Hertz. So there was quite a difference between the two of them. So what happens to the n+1 rule when the two protons that it's got 2 neighbors, but they're not the same? So how does this manifest itself in a spectra is, I guess, what I'm trying to talk about. And so for when you've got protons that are not equivalent, you can't rely on just the simple Pascal's triangle of one or doublets, triplets, quartets in such a fashion. It doesn't work because the coupling constants are different. So what we need to do in situations like this is use what we call a splitting tree. And what we'll see is that splitting trees, Pascal's triangle actually is a splitting tree, but because the coupling constants are the same, it comes out as really simple doublets, triplets, quartets, and that sort of thing. So if your proton HB, and you would normally resonate right where I'm drawing this line here, and you're split by 2 neighbors. The first one for the trans coupling, we'll just split it, say like this. And the difference in Hertz across this value here would be, say, 14 Hertz. So this is a trans coupling. So if you only had one proton and it was trans, it would appear as a doublet because you'd have one peak here and one peak there. Let me get my laser. One peak here and one peak here. So that would be, if it was just a simple, there's only one proton there. But that's not what we have. We've actually got another proton. It's the cis variety. And let's say that this would be split again for the cis. So each line would be split again, and I haven't really drawn it nicely to scale. But let's say that the cis coupling turned out to be 6.5 or 6 hertz. It was on the low end. Then stop that. This peak would manifest would be as a series of, I made that a bit, let's put that there. A series of lines that would have a height of 1 to 1 to 1 to 1. And we would call this a doublet of doublets, because it's been split twice. So it's been split once by proton B, has been split once by HD and once by HC. So this coupling here, this trans coupling would be JHB HD, and this coupling here would be JHB HC. And it would, so you'd actually show up as four heights of equal, 4 peaks of equal height, a doublet of doublets. So we would use that's basically a splitting tree. Now, if you go back to, if we just return to the Pascal triangle case of over here, where these 3 protons all appear as a triplet because of this proton and this proton. The way that Pascal's triangle actually works is that how it would actually is that, so if this is where you would normally, your normal chemical shift, you're split once at, say, 7 hertz, and then you're split again at 7 hertz. The only difference, though, is that you'll notice that here, this center line has been fed once in this direction and once in this direction. So it's got a height of so it's twice as tall as the other peaks. But the actual coupling constant here would be 7 hertz on each side. So for all of these sort of Pascal triangle sort of things, it is a splitting tree, but the thing is that the peaks that are higher than 1, they're reinforced multiple times. So that's basically, this is what happens when you've got protons that are split by multiple protons that have different coupling constants. So you'd use a splitting tree. And this is actually, in many ways, this is more common than not. Like, this is a relatively common sort of manifestation, in particularly if you've got a complex molecule. What's the next? So if that's the case for HB, first of all, any questions on that at all? Okay, well then I'll ask this question. So what should HC appear like? How many protons would it be coupled to? This guy. Yes, that's correct. 2. So it's coupled to 2 protons, right? So HC is coupled to HB, and that's a cis coupling. It's a vicinal coupling. Do we remember the type of coupling when you're on the same carbon as, because HC and HD are on the same carbon. Do we remember the type of, it was a special name for this. It's a 2-bond coupling, so it'd be a J2, but it's got a special name. So a J3, which is 3 bonds, 1, 2, 3, is called vicinal. I'm probably spell it wrong. But what was the 2-bond coupling called? And think of 2 in an astrological sense. Which constellation has got 2 of whatever it is? I see nobody is born in May or the early stage of June. Okay, so that would be, when it's a 2-bond coupling, that is geminal. Right. And so geminal coupling on double bonds is actually quite small. It's quite low. So it's around 2 hertz or so. So if we were to do an analysis of HC, the way it would look would be as follows. So it would normally resonate around here, and it would have a large coupling of, well, quasi-large coupling of around 6 hertz. Maybe made that a bit too big. 6 hertz. So that would be the JHCHB pre-bond coupling. And then there would be the smaller 2 hertz coupling in here. 2 hertz. 2 hertz. And this would be the geminal coupling, the 2J HCHD, I guess. And so this spectra would also appear as a doublet of doublets. So it would be a doublet of doublets. And the height would be 1 to 1 to 1 to 1. And so the neat part is for this is that if you ever wanted to, if you ever are, if you're ever looking at something and it's got 4 lines and they're all relatively the same height, one of the way that you could, the space between here and here should be equal to the space between here and here. And that will be 1 coupling constant. And then the space between, say, here and here, or here and here, should be the 2nd coupling constant. And that's, yeah, that's basically how you would look at that. And same sort of thing up here, that 1 coupling constant would be the space between here and here. And the other one would be 1st line to 3rd line, 2nd line to 4th line. And you would, there'd like, the chemical shift could, like some of the spectrometers, they will measure this in hertz as well. And you can just do a subtraction to calculate what, how many hertz or the distance between the two peaks would be. Yeah, I feel like Dave Matthews song coming on, so I stopped saying space between. What was the next thing? So, and you could do a similar sort of analysis of HD. The difference would be that it's going to have the same small geminal coupling, and it's going to have the larger trans coupling, but it would also appear as a doublet of doublets. So these are what we would call splitting trees, and they are used when a proton is coupled to protons with different coupling constants. So it's kind of a neat little exercise to do. So the integrals for each one of these the chemical shifts for all of these would be slightly different as well. And so they would all integrate to 1. That would be what we'd expect. Let's see here. One of the things that Jeff brought up in the last class dealt with on our spectra, which we were looking at. There was a peak way down here at 1H that represented the hydroxyl proton, and it came out as a singlet, and it didn't couple with the protons that were on the carbon, which we would have expected, because protons on carbons, they do couple with their neighbors, right? And so there was a question about why there was no coupling to that proton. And that got me thinking about hydroxyl protons in general. So we should probably, acidic, we'll just call these acidic protons. So protons that are bonded to oxygen, nitrogen, to a lesser extent, sulfur, if you got those. The most common, of course, will be the OH protons. There's a trick you can do, a common experiment in NMR called D2O exchange. So let's pretend that we've got ethanol. Let's use that as our spectra. So if we had ethanol, so CH3, CH2OH, and we ran the spectra of this, how many signals should we see? Nobody? So we should see a grand total of 3 peaks, right? So we should have, we'll call these ones A, B, and C. B should appear at what type of multiplicity? B should be a B has got 3 neighbors. 3 plus 1 is 4. So B should show up as a quartet. And A, which has got 2 neighbors, 2 plus 1 should show up as a triplet, right? Because N equals 3, N equals 2. Okay, and of excluding the proton and the hydroxyl group for a second, of B and A, which one should have a higher ppm and be de-shielded the most? Which one should be de-shielded the most? Right, because it's next to the oxygen, right? So electronegative atom. So our little, our if we wanted to just draw this, I'm just gonna sort of guess here, something reasonable. We would have a triplet somewhere around 3.5 ppm, I'm gonna guess. And we should have a quartet down here at maybe 1.9 ppm, I'm gonna guess. Let's draw our integrals. This will integrate to 2H. This will integrate to 3H. And our proton on the oxygen. Now this is interesting. Where it shows up is entirely, it's because remember on our correlation chart, it went across a wide range of values. There's a couple of reasons why it happens like this. One of them is the fact that it depends upon the concentration of the sample, concentration. So it's very similar to infrared. So if you've got a really concentrated sample and you're running it, the hydroxyl group can hydrogen bond, right? So, and if you get a series of the hydrogen bonding, H bonding, if your sample is really concentrated and you've got lots of hydrogen bonding, it's going to shift the chemical shift to higher ppm. So H bonding, if it's concentrated, it'll shift to higher ppm. If it's not, because you've got oxygen, which would be with hydrogen bonding to it, withdrawing electron density, and so it's going to be basically at a higher ppm. The other thing it's going to do is it's actually going to broaden the signal when it does this, because the so it won't appear as a nice little sharp line anymore. It starts to appear as sort of like a broad sort of singlet, because is a broad shape, because what's the best way to describe this with because the energy difference between the two energy states is, because protons are going on and off because of the hydrogen bonding, it's less defined, and it starts to broaden the shape of the starts to broaden the shape of the actual peak. And because it's broadening the shape of the peak, the protons actually on the carbons next door don't sense it as much. So that's why it really doesn't couple. So you rarely see coupling with OH protons. But the whole point of this experiment where I was starting for was D2O exchange. If you run your sample in chloroform, and let's say that it was a relatively concentrated sample, we had a peak over here, let's say 4.1 ppm. That did integrate to 1H. If you run it in chloroform, so your samples run in CDCl3, and then you take it out of the NMR and put a drop of deuterated water in there and shake it up and run the spectrum again, what happens is that OH peak just disappears entirely. So after you add D2O, shake it up, and you run the experiment, you end up with the spectra minus the OH peak. So 2H, 3H. And the reason why this is that the deuterium actually exchanges with the OH group. So if you've got your carbon here, you've got some deuterium, and it's hydrogen bonding. Things like this can basically happen. So there's an equilibrium which is established, and some of the carbons, eventually all of them, will now be bonded to deuterium. And deuterium's got a different I number, so, and it resonates in a different, completely different energy level, like different, it's totally outside where you'd be doing your, sending your packets of radio waves. So it's completely outside of that area. You need to, if you want to run a look at deuterium, you've got to program it to basically look at a different region of energy to actually get it to work. So D2O exchange, basically acidic protons can be exchanged using deuterium, and they are removed from the spectra. And that's a way of determining which ones are hydroxyl groups or carboxylic acids, that type of stuff. So in the example we gave, the peak was relatively sharp. And so if the hydroxyl group peak is relatively sharp, that's one thing that's telling you, is that the sample is quite dilute, because there'd be no H bonding going on. But it's, yeah, so, but anyway, so deuterium exchange is so often on examples, there'll be a, you know, here's your spectra, the peak at 4.1 disappears after adding D2O. What that's telling you is that's an OH group, an OH proton. There was one other little thing. Right. And I sort of drew this. Another thing which manifests sometimes in spectra is that and I sort of drew that right here. Come on. Is often the peak heights aren't exactly perfectly so it's supposed to be 1 to 2 to 1, or 1 to 3 to 3 to 1. Sometimes spectra, when protons are coupled to one another, they sort of angle in the direction that where the proton they're coupling to. And this is called multiplet skewing. It's just a the outermost lines tend to have unequal heights, and they sort of point in the direction of where the proton, the other proton that they're coupled to, happens to be on the spectra. It's just a odd little artifact that people have noticed. So don't be, sometimes the inner peaks can be slightly higher than what you would normally expect. It doesn't happen all the time. It's just an oddity that I thought I'd bring to your attention for some crazy reason. At any rate, so that was the last little bit of the proton stuff I wanted to talk about before we moved on to carbon. Were there any questions at all? I guess the real important part is the splitting tree and the deuterium exchange. Just a simple experiment that you can just shake up with a little bit of deuterated water, rerun the spectra, and all the OH protons will basically just disappear entirely. Okie dokie. So did anybody do the last unknown from last class? Do we want to go over it right now, or do I leave it for you guys to do on your own, and then later on you ask me questions about it?
I'll be okay with going over it right now.
Okay, so let me find it. Does anyone have a structure they'd like to propose? Okay. I will stop sharing my screen for a second and I will find that spectra. Let's see here. Alrighty, here we go. Let's get rid of this. So question 4 at the bottom here. Let's see if we can make this bigger. Okay, so what's going to be the first step?
Getting the base formula?
Right, okay, so draw. Now, calculator. So we've got C11H18 contains one heteroatom, has a strong absorption at 3251. So 3251, where is that in the range of? In the infrared.
OH.
OH, right, OH. So that means we need to put in a oxygen. Okay, so oxygen is, stop that. Oxygen is 16, so this would be C1H4. So C10H14O. All right, and then, so that will be the formula. What would be the next step? Yes.
Double bond equivalency.
That's right. So DBE 10 minus 7 plus 1 equals 4. So 4 is a good chance that it's an aromatic. And the protons of an aromatic, do you remember where they come out? So they come out between, say, 6.5 and 8, right? So they come out in this range, basically here. Usually and depending upon the substituents, it's, yeah, like they'll be, the low end will be around 6.5. The high end will be 8. I think if you get some really electron withdrawing groups on there, you can even pull it a bit further. But these two protons here are right in the aromatic region. So that looks like that's a real good little check mark. And so then the next step, what we would want to do is we'd want to make our little correlation table. And we've got on our, we've got just stop drawing here. I want to be able to move my little, we got peak down here around 1.4. We've got a peak at around 5, and then these two around 7. So the next step we would do is the little table to check out the neighbors and that sort of stuff. With regard to these peaks here, this is going to be these two aromatic peaks. Yeah, we'll start class on Thursday. We'll just finish this off, but give it a crack. You, in the infrared, we could use the out of plane bands to determine if it was ortho, para, meta, that type of stuff. There's specific patterns that are common in the aromatic region, and we sort of did that last class when we were doing the top hat questions, like what should you expect to see. So this peak of a doublet and a doublet's distinctive for a certain class of substitution patterns on an aromatic ring, and we'll do that at the start of Thursday. And it looks like this peak here, this broad peak, this will be the OH peak. And then there's another peak down here, which equates to not, it's a singlet, which equates to 9 protons. And that's a distinctive type of substituent because you need 3 methyl groups that are all exactly the same. So there's one group which fits the bill perfectly for that. So yeah, we'll go over this at the very, very start of Thursday's class. I've got to run to a little, I got a meeting in like 2 minutes. Were there any quick questions to answer before I run off and leave you? Okay, if not, I will leave. And then I'll process this video and I'll put it online so you can listen to it again if you want to. All right. Well, I hope everyone has a good day. And we'll see everybody on Thursday at the latest.
Thanks. Have a good day, Dr. Hill.
Yeah, you bet.
See you Thursday.
You bet.